The enhancement mode MOSFET looks like this. So, you are already familiar with this bit, which is the MOS capacitor. Okay. So, if you look at this cross section, if you forget everything else that is present beyond this, if you forget all that, what you have here is the gate, insulator, semiconductor and the back contact, and this was your MOS capacitor. But what the MOSFET does is it makes use of this device, but it adds some more terminals. Okay. So, now you have the gate, which is provided a gate voltage Vg, okay, and then you have the back contact, which has got a voltage Vb, and this back contact is now called, in the context of the MOSFET, it is now called the body or the bulk contact, because it connects to the body of the semiconductor. Okay. So, it is the body or the bulk contact, and then that is your familiar gate contact, that is connecting to the gate metal. You have your insulator, and the insulator could be an oxide, and it has got some thickness T ox, and it has got a permittivity epsilon ox, and therefore, the insulator capacitance per unit area is epsilon ox by T ox. And then you have your semiconductor, and let us stay with the example of a p doped semiconductor. Now, in order to create your A and B, that is the two terminals through which the signal has to transfer, the signal has to transfer from A to B, and in order to have those two terminals, you have your source and you have a drain. Okay. So, these are two additional terminals in your that are added to your MOS capacitor to create your MOSFET. Now, what does the source and drain have? Now, the first thing is that the source and drain, let us look at the way it is created. Okay. So, it is not just metal placed on the semiconductor, okay, and we will see why it should not be. Essentially, what we need is a electrical contact, and the current will actually transfer from source to drain, okay, or the carriers will move from the source to drain, or vice versa, depending on the type of carriers and depending on the potential. And the first thing about the source and drain is normally they are absolutely symmetrical. There is nothing to say as to, there is nothing in the design or in the fabrication to say that one of them is the source and the other is the drain. The source and drain are purely defined based on the voltages that you apply, the bias voltages that you apply. Okay. So, this structure is absolutely symmetric. So, given a MOSFET like this, it is equally possible to treat this terminal as your source and that terminal as your drain, it does not matter, but it all depends on the voltages that you apply. So, we will just label that as your source, and it is given a source voltage Vs, and this is the drain, and this is given a drain voltage Vd. Now, all these potentials, that is Vb, Vd, the gate, are all taken with respect to the source. So, this is the reference potential for your MOSFET structure. What is important in the MOSFET is the gate to source voltage. Okay. So, it is not just Vg with respect to some arbitrary ground or some universal ground, that really you need to really extract out what is the potential seen or what are the fields seen within the device, and therefore, all the voltages are measured with respect to the source. So, you have the gate to source voltage, which is basically Vg minus Vs. You have the body to source voltage, which is basically your Vb minus Vs, and you have the drain to source voltage, which is Vd minus Vs. Okay. But for now, let us just say that the source is at Vs and the gate is at Vg, the body is at Vb and the drain is at Vd. So, how are the source and drain terminals created? So, you have a metal contact for us to have interconnects on the outside, but then the metal interfaces directly with an N doped semiconductor, a very highly N doped semiconductor. I should probably put an N plus there. Okay. So, look at the structure, you have a p doped semiconductor as the basic body. Okay. So, that is your substrate in some sense, and then when you are going to create the metal contacts, you have strongly n doped regions, and then you have your metal contact. Okay. So, essentially you have created a diode here, you create a diode here and you create a diode here, and then you have your metal contact. Okay. Now, what is the purpose of this source and drain? Okay. So, the idea of the MOSFET is to operate in inversion. So, the MOSFET, if you think of the MOSFET as an on and off device. Okay. So, when it is off, let us say the flat band voltage is 0. So, we are familiar with the MOS capacitor and the flat band voltage. So, let us say the flat band voltage is 0. Okay. And theoretically, when my Vg is at the flat band voltage, or generally speaking, when Vg is less than Vt, there should be no electrons here, and therefore, you are in depletion mode operation, or you are switched off. Okay. So, there is nothing, there is no way carriers from the source can actually move to the drain, because this region is completely depleted. But when Vg becomes greater than Vt, the MOSFET enters a inversion region, which means that minority carriers start appearing at the interface. So, we have already looked at this in the discussion on the MOS capacitor. And the idea is that if you have an n doped region, not these minority carriers, which are electrons, not only appear from the thermally generated carriers from the p doped bulk, but are also drawn in from the source side, provided that there is a drain to source voltage. So, the source also contributes to these. So, the essential idea, so this is the first role of the n plus doped source and drain, okay, which is to act as a carrier source, okay, or the minority carrier source in the device, and essentially create this n plus electron, n plus pathway, or this conduit, okay, because everything around this is doped, is all depleted, sorry, it is a p-n junction device, therefore, this is all depleted, you have a depletion region throughout here. Okay, so, all this is depleted, but when inversion happens, you have this entire region being depleted, and you have an electrically conductive path from this n doped region through these electrons and through that n doped region into the drain. So, that is the way the MOSFET intends to operate. Okay. So, that is one point of having a n plus region. The other key purpose of this n plus doped, why are we insisting on a heavily doped drain and source contact? Okay. So, this is your drain source contact. The idea is we want to inject a current, right, from this metal and into that metal, which means that we want this metal semiconductor junction to be ohmic. Okay. So, if you remember your metal semiconductor junctions, we could have two kinds of junctions. One is where we had a Schottky barrier, and the other is where we had a ohmic contact. Okay. So, which contact would you like if you want to have current flowing through both ways? We would ideally like an ohmic contact. So, by simply choosing a metal and by doping the semiconductor correctly, we should have an ohmic contact, but unfortunately that is not, it is not that trivial, and it is not that trivial because of a lot of issues, particularly because of the Fermi level gets pinned because of interfacial states, etc., which means there are trap states here, electrons get trapped and electrons cannot move about very easily. So, it is very likely that we will end up creating a Schottky barrier or a Schottky contact, okay, and this is not what you need. So, how, given the fact that you can do nothing other than create a Schottky contact. So, let us say we have this problem, we can only create a Schottky contact and we want to get electrons in and out of this from the metal to the end to the doped semiconductor, which is a source. We want to get electrons in and out of this. How do we go about doing that? Okay. So, let us look at the band bending of a metal semiconductor junction, Schottky junction. So, let us say that is your band bending. Okay. Now, what happens if I increase my dopant concentration in the semiconductor? If you increase the dopant concentration in the semiconductor, the band bending will become a lot sharper. It will be, the bending will be much more narrower, right. All the bending will finish quite early, the XT becomes small, the bending becomes, the bending is very, the electric fields are quite large, etc., etc. On the other hand, if you reduce the dopant concentration, the bending is more relaxed, the XT is much larger, the electric fields are weaker, and so on. But the advantage of having a bending that is very sharp is that if you remember the different mechanisms of charge transport through a metal semiconductor junction, we had thermionic emission, we had diffusion, but we also had tunneling through the barrier, through this triangular barrier, we had this WKB approximation, etc., etc. So, the point of having this heavily N plus doped region is to create a sharp triangular barrier through which electrons can easily tunnel in and out, okay, and therefore give you a very low resistance contact between the metal and the semiconductor. So, that is the reason for having this N plus doped region. Apart from very obvious reasons, it is good to have a strongly doped source and drain contact. So, these two together, that is this metal and this doped region together make your source. So, essentially the potential here is the potential here. So, all this is short circuited, okay, and these two together make your drain. Okay. So, now let us look at some of the geometrical aspects of the MOSFET architecture. So, we have, so this is the MOS structure. So, you have the back contact which is at VB, the source which is at Vs, the drain which is at Vd, the gate which is at Vg, they have an insulator between the gate and the semiconductor, and all potentials are taken with respect to the source. So, what is important is VDS, VGS and VBS. Okay. So, what are the geometrical aspects? Now, this region between from where the source ends to where the drain begins, okay. So, in that sense, so this region, okay, the length of this region is quite important and it is called the channel length. It is a technical term, okay. So, when we say channel length, we are talking about this distance from the drain to the source. That is the length the electrons or carriers must travel if they want to go from the source to the drain. Now, the channel length is quite an important parameter. So, when you hear about Moore's law and when you hear about scaling, when you hear about the technology, the MOSFETs and the transistors becoming smaller and smaller, it is the channel length that they are trying to reduce, because if you reduce channel length, the speed of the MOSFET is expected to increase. Okay. Of course, they are reducing all the other parameters also, which we will look at when we talk about scaling, but it is a channel length that if you reduce the channel length, you generally tend to improve the speed of the MOSFET. The other parameter is as to how wide this device is, right. So, you have the same cross section through the page. So, as you look inside the page, you have a certain width. If you look at the perspective view, the device is, has got a certain width, okay. So, that will be your gate and so on and so forth. So, that will be your contact and that is your semiconductor, etc. So, I have not drawn it in perspective. So, you are looking at a cross section, but the device has got a certain width and that width is called as a channel width, okay. So, that is the width of the channel. And that is given a symbol W. So, when we say W and L, we mean the channel width and the channel length. And a special ratio, okay, which is particularly useful when we talk about currents, etc., in the MOSFET, is the ratio of the channel width to the channel length. Okay. So, this ratio So, the ratio which is basically W over L, right, W by L is the channel width of the MOSFET divided by the channel length, and this ratio is particularly important in the context of device design or circuit design, and it is given a special name. It is called as the aspect ratio of the device. So, when we say aspect ratio, when you say the aspect ratio is 1, it implies that the channel width is equal to the channel length, and when we say aspect ratio is 2, it implies that the width is twice that of the length, and so on. Okay. Now, that is the channel length and channel width. Now, apart from that, another important parameter with regards to frequency response in particular is the overlap length. Okay. So, the source and the drain, they extend below the gate. So, the gate can impact a certain region of the source and the drain. So, if you look at this cross section, you can see that the gate metal is overlapping the source and the drain. Of course, there is an insulator in between. So, there is no direct current unless there are leakage currents. There is no direct current from the gate to the source and drain or vice versa, but there will be a field impact. Okay, any voltage in the gate will try to influence these regions at the source and drain, and this length of this overlap is something called as the overlap length or the gate to source overlap length and the gate to drain overlap length. If these two are symmetrical, we will just say both of them are L overlap. Okay, so, this essentially becomes a little capacitor, right. So, what is the capacitance of this capacitor? So, it is epsilon A by D, but what is epsilon? It is epsilon ox. What is the area of cross section or what is the overlap cross section? It is L into W. So, L overlap into W is the overlap length into the width of the device is the area of cross section divided by the thickness of the oxide T ox. So, that is the overlap capacitance, which is the capacitance between the drain and the source. Now, there are many other capacitances because you have two PN junction diodes. So, therefore, there is a diffusion capacitance or a depletion capacitance, etc., but we are talking about the capacitance of this device, this structure here. Okay. So, that is to do with the general architecture or the design of the MOSFET. Okay. There are many other small features, but I mean these are the basic points. All right. So, this structure has got what? It has got a p doped semiconductor and it has got n doped contacts, right, strongly n doped contacts. And the idea is when you have inversion, you will have electrons which are the minority carriers between the source and drain, and you will have an electron channel going in from you will have electrons being the current carriers between source and drain. So, this device is called an n channel enhancement mode MOSFET. N channel means it is the electrons that are going to form the channel. So, this region is called as the channel. Okay, so, that is the channel which is the conduit of charge transport. So, it is an n channel enhancement mode MOSFET. We will simply call it as NMOS device or n type MOSFET or n channel MOSFET. Similarly, you could have the counterpart, the complementary device, which is the p channel MOSFET, and for the p channel MOSFET you have to have a MOS capacitor with an n doped semiconductor and you have p doped source and drain contacts, and the idea is in inversion you will have holes at the interface which are the minority carriers, and you will have holes being the carrier of the current. You will have a hole current going from the source to the drain or from the high potential to the low potential, and everything else remains the same. You have a channel width, you have a overlap length, and you have a channel length. Now, there are different kinds of field effect transistors. So, I have taken this from an online source, okay, And these are the circuit equivalents. So, if you want to represent them as a circuit, so these are the ways you would represent these transistors, but we are interested in the enhancement mode MOSFET, right. So, we are interested in these 6. You have any of these options, okay. So, you can use any symbol you like, but if you are using, let us say you want to represent the body contact or the bulk contact, and you want to set the body or bulk contact at a different potential from that of the source. So, normally we connect the body and the bulk to the source, but it can be used in a more clever manner by creating a potential difference between the body and the source. So, if you want to really use it that way, you want probably using this symbol. It shows the gate, it shows the drain, it shows the source, and it shows the body here. Okay, so, that is the body terminal, and here what it is telling you is that the body is connected to the source. But what I will be using is typically this. So, this is just as a force of, by the force of habit, I tend to represent N channel devices like this and P channel MOSFETs with a circle there, and that circle is probably comes from the use of the NOT logic, okay, or the inverse logic. So, that becomes your PMOS device, that is your NMOS device. You can't see the bulk contact in this. Okay, so, that could be your drain, source and gate, and these are your 2 devices. Okay. And this is yet another representation for the PMOS and the NMOS, but let us just stick to one, we will just stick to this particular representation. So, here we have the NMOS and here you have the PMOS. Okay. So, in the NMOS we have the drain terminal, you have the source terminal and you have the gate terminal. The body contact is not shown here. Okay. Now, the gate is at potential Vg with respect to some, let us say, universal ground. The source is at a potential Vs with respect to the same ground, and this is at a potential Vd. Now, what is important with regards to the MOSFET are these potentials, because that is what determines the electric fields inside the device. So, it is the gate to source potential, which is Vg minus Vs. Okay. So, when we say Vgs, it means it is Vg minus Vs, or automatically the gate with respect to the source, and when we say Vds, it means it is the drain minus the source potential. So, that is Vds. Similarly, for a PMOS, okay, you have the source, the drain and the gate, and the reason I am relocating the source here is if you think of it from the point of view of a circuit. Okay, so, I am trying to sort of establish that thread right now, which is typically for an NMOS, you will find that if this is the construct, you will find that this is at a higher potential, everything is with respect to the source. So, this is at a potential that is greater than the source, the gate is at a potential that is greater than the source. And in the case of a PMOS, you will find that if you want to continue using the same equations without changing the variables from gate to source to gate, etc., you want to be gate to source to gate to drain, etc., you want to sort of relocate these variables in a manner where the source is at a higher potential, the drain is at a lower potential, and the gate is at a potential that is greater than the drain. Okay. So, you will probably gather this intuition as we move along, but nevertheless that is the reason why I am just relocating the source here. Okay. It is basically the opposite kind of carriers. Okay. So, it is the holes, it is the holes which are carrying current, okay, and the whole current is moving from the higher potential to the lower potential. In this case, it is the electrons that are carrying current, okay, and the electron current is moving from the lower potential to the higher potential. So, in both cases the source is sourcing the carriers and the drain is accepting the carriers. So, if you want to think of it that way, then that is another way to look at this. Okay. So, that is the source, this is the drain, and that is the gate, and what we are interested in is in the gate to source voltage and the drain to source voltage. So, if you recollect, if I tell you that the source is at a higher potential than the gate and drain, you will know that the VGS and VDS are negative in value. Okay. But these are the important voltages and these are the circuit symbols we will be using for the NMOS and PMOS. The big difference in the PMOS is this little circle that you see at the input. Okay, so that is the difference.